Hey everyone, welcome to class. In this lecture, we're going to be focusing on our first unit of real inferential statistics. This lecture is going to be on t-tests. So moving into the world of inferential statistics, we're thinking about that guest lecture that we had with Professor Mario, and we're thinking about the normal curve as the basis of our probability theory, right? The normal curve shows the distribution of our data and allows us to kind of make jumps or claims about the patterns in our data because we know certain things to be true about the normal curve. The normal curve in a lot of ways helps us standardize our data and make comparisons. And we're going to use that normal curve, like I said, to see if our data that we have is at random, right? Or if there's actually a pattern and we have some evidence for our hypotheses. So this will be made a lot more clear and concrete as we start to actually move into operationalizing these tests. So t-tests we're going to start with because it has a lot of continuity with a lot of the work we've been doing in terms of calculating means and standard deviations. Because the t-test allows us to compare the means of two different groups, right? These groups are independent, and the image below just shows you that we're going to be comparing that average value and that distribution, right, that line, to see if these groups are actually systematically different from each other, or really they're just kind of the same. So let's put this in context of a hypothesis that we've been working with in our previous homeworks. So a lot of folks did some hypothesis like there is a difference between political science major versus non-major scores on the midterm, right? So say students are taking a political science midterm, maybe it's Intro to American Government, where that course has a lot of majors and non-majors in it. But we maybe might think that because the major students are a bit more interested or invested, they're going to be doing better on those tests. So we need to be able to systematically determine whether or not there is a pattern in the data and whether there's some evidence for this hypothesis. We can look at the means kind of on their own, but we really can't say anything without doing some additional kind of probability theory using the normal curve to determine whether or not these things are actually happening at random. So within the parameters of t-test, we can only do non-directional stuff, right? So we're going to say there is a difference between political science majors versus non-majors. We cannot, under this circumstance, say there's going to be an increase or a decrease, right? So we're not in the world of directional, only non-directional. The kinds of levels of measurement we're going to be working with are for the independent variable, we're going to have a binary variable or a categorical variable. And then our dependent variable is going to be interval ratio or numeric, which makes a lot of sense, right? If we're comparing the differences between two groups, that grouping variable has to be categorical, right? So we need to have a way to split the data. And then the midterm score, right, is going to be interval ratio because we're comparing the means between two groups. In order to get a mean, we have to have interval ratio. So I think if you think through the intuition between of our hypothesis and what's happening in a t-test, right, if we're comparing means of two groups, to have means, we have to have interval ratio. To have groups, we have to have categorical. Okay, so our hypothesis and our working hypothesis is going to be comparing the means of the different majors' performance on their midterm. This is going to be largely using R, which is part of the reason why we took a little bit of a step back, pumped the brakes, made sure everybody was ready to kind of move on to this unit because we're going to be showing you how this works in R. This is going to have code embedded in it. So one thing I'll kind of plug here right now is this whole slideshow is made in RStudio. RStudio is really flexible and really powerful. And so I was able to actually embed the code that you guys are going to get access to calculate your t-test. Along with, I'll give you the slides. And if you want to try to knit them yourself, I'll show you how to do that. But this is all going to be happening in R, and then I'll show you kind of the analog old school way to do it. I won't make you do it that way, but I want you to understand what's happening under the hood when you're doing this in R. Okay, so let's just start by looking at some averages, maybe in the same way we were doing in our homeworks, in our midterms. So we're going to do two different things to start in our code. So don't look at this, these upper 2 points. Let's start with the code chunk. So we're going to load two different libraries, right? We're going to load our tidyverse library and the Haven library in order to read this SAV file, this SPSS file. Again, so When you import your data set with that drop-down menu, it's going to run this line of code under the hood, right? And it's going to find the path. The path is just where on your computer this data set is stored. So it's probably in your downloads folder. And so this read SAV function is going to take the path that you specify in the import data function and bring that into R. So this path in read SAV is unique to you because it's unique to where it's stored on your computer. So remember, if this line of code doesn't work for you, it's because it's not supposed to, it's not your computer, right? So just know you can put your line of code that comes out with the import dataset function in this in order to get it to knit. You have to have this in there for it to knit. So next time you import your data set, so in this case, for this one, we're going to import an SPSS file. Look at what happens in the console after you clicked import, because the console will actually show you the code it ran to get it in there. But a lot of times I think we're just importing and moving on. Just look at the console next time, because you'll actually be able to see the path that are used to find this data set. So just a little plug for that, for you to kind of be thinking ahead on what happens when you're actually using that import dataset function. Okay, let's calculate the mean in the same way we have been consistently, right? So we're going to use that mean function. And because we're not using any pipes or anything like that, we're going to use the $sign. So we're going to select from student data the midterm, right? So we're going to get just an average of the midterm scores. Okay, so the average midterm score was about 58%. Not great. But we think that there might be a systematic difference between the majors and non-majors. So we think that maybe the majors are going to be doing better than non-majors. So let's write some code in order to get at what we think the average is for majors and non-majors. So we're going to move to the next slide. Okay, so using the tidyverse code that I've given below, we're going to use the pipe function, right? So this is our little percent, %, to pipe in the student data. So our first line of code is piping in the student data. We're then going to group by majors. The group by function tells R how you want to split up your data set in order to put the next function in. So group by is going to be major. And again, we're not using the $sign in this particular case because we have a pipe. The pipe essentially circumvents the need for the $sign in later code, which just makes it a lot easier to read. So remember, if you are using the $sign in the group by and summarize at, you don't need to be. But if you don't have the student data piped into all of this, none of it will work. So this pipe workflow makes it a lot more human readable. It's called human readable workflow in the coding community. And it's really important in terms of having other people be able to read your code. And so I want you guys to get familiar with pipes along with just the typical $sign operator. So we are going to be piping in the student data, grouping by majors, because we want to find the averages for each major group. Remember, major is 0 and 1 binary. If you are a 1, you're a major of political science. If you're a 0, you're a non-major. And then we're going to use the summarize at function to use or to select the midterm variable. And then we're going to get the mean and the standard deviation. Okay. So the summarize function takes multiple arguments. The first argument is what variables you want to use. So it's going to take vars midterm. Vars just is a function that helps you select the midterm or select a certain variable. So summarize at vars midterm selects the midterm column, and then we're going to find two different values for it. Within this list function, we're going to select the mean, and we're going to call it mean, and the standard deviation, and we're going to call it standard deviation. So you can find the mean and standard deviation, and it wouldn't name them here down in your output, but we want to name them so we know what each of them is. So when we run all of this code, which I'm going to give to you for you to run for yourself, you are going to be able to see that the mean for non-political science majors is 48.7, and the mean for political science majors was 62. If you just look at this, you wouldn't be able to see that there might be actually some differences between the performance between majors and non-majors. And so we have a little bit of evidence here, right? But we can't be actually sure if this is just based on random chance. Maybe the majors just did really well this time and it was a one-off thing. So we really aren't 100% sure this is a systematic pattern at this point. So we need to do inferential statistics in order to be sure and have some evidence for our hypothesis. So we're going to move on and talk about inferential statistics. So again, this slide is just to reiterate that it seems like we have some evidence for a hypothesis that majors have an average of 62.4 and non-majors have an average of 48.7. So it seems like political science majors are doing a bit better. So we can calculate a t-test. The formula is shown below. You can, in theory, do all of this by hand, right? So remember, our X bars are our averages. So this just means the difference between our first group average and our second group average. Remember, the N's are just the amount in each of those columns. It's the dimension of the column, so how many there are. And the S is our standard deviation for each group, right? The little subscript, the 1 and the 2 is just which group we're talking about. So in theory, you could do all of this by hand. It's actually not all of the outside of that scope of what you guys could in theory do. But part of the reason why we love things like R is it does it for us, right? And so let's make our lives a bit easy and we'll move into the world of R versus doing this by hand. We also are going to be finding both the critical value and our test statistic, and we'll talk about that moving forward. So using our t-test and the hypothesis, we're going to use, so the hypothesis is there is a difference between major and non-major performance on the midterm, and we're going to use the t-test function. The t-test function allows us to calculate our t statistic along with a bunch of other helpful info. Okay, let's break down the code a little bit to start. So the t-test function, right? So t-test with the parentheses is going to take 2 different variables. The first variable is going to be our dependent variable. That dependent variable is our interval ratio variable, a midterm, right? So our dependent variable is going to be midterm, and then we're going to use a tilde sign, okay? So the little wiggly line, it's called a tilde, and we're going to specify our independent variable after that, which is major. So on the left-hand side, we have our interval ratio, and on the right-hand side, we have our binary grouping variable. If you flip these, your answers are going to look weird, right? So you have to remember that our DV or our interval ratio is on the left, and our IV, our binary, is on the right. Okay, so in this tilde notation with our dependent variable on the left and independent variable on the right, you're going to see that very consistently, actually. It's the basis for a lot of it's linguistically the basis for a lot of our testing in R. So when we get to regression and a lot of these other things, we're going to keep seeing the tilde. So just kind of keep that in mind. And again, we're using that $sign because we're not piping anything in. And so we're going to select from the student data set both the midterm and select from the student data set the major variables using the $sign. So when we run this line of code, we get this output. Now there's a few different things I want to draw your attention to early on. If you go to the very bottom, we're going to have the mean for each group. The mean for group 0, which is non-majors, is 48.66. The mean in group 1 is 62.44. Does that look a little bit similar? It actually just calculates it for you within the test statistic, right? Because we're comparing to 2 different means, and then we're going to use some inferential statistics using the normal curve to be able to decide whether or not we think this is happening by chance. Okay, so the other interesting things that we're going to get here, the T over here is our test statistic. Okay, so it's negative 3.109. So we'll talk about what that test statistic means more concretely in a second, but this is where you find it. So you get the test statistic is negative 3.109. We also get this thing called degrees of freedom, which is a kind of like a catch term for the kind of variance and the how big our data set is. We'll talk a bit more about what degrees of freedom is later. And then we get a p-value, which is going to be our threshold for statistical significance. And we'll talk about that in a future lecture. But that is going to be our threshold for whether or not we can decide we can either reject our null hypothesis or take some tentative evidence for accepting our alternative, right? Okay, so we'll get into this a little bit more concretely. Our test statistic in this case, our t-value, is -3.109. So under the hood, we're calculating this test statistic, and R is then going to be comparing it to things that we know about the normal curve by finding a critical value using our degrees of freedom. So the degrees of freedom allows us to assess whether or not our data is at random and helps us find this critical value. And then since we're working with two tails of the normal curve, we don't have a directional hypothesis. We're using both. We're going to use a two-tailed test. Now, that's not as important for you guys to lock down. Just know that we're using a two-tailed test because we don't have a directional hypothesis. So let's talk about finding that critical value and what R is doing under the hood. So we know that our degrees of freedom here is 21.027, right? This is this line under the data argument. Degrees of freedom is 2.1027. So old school stuff, we would find our degrees of freedom, 21.07, and then pick a statistical significance threshold that we wanted. So if you look at the very top few rows, it says the cumulative probability, one tail or two tails. We really want to be using two tails because we have a non-directional. And then the conventional threshold that we use is 0.05. And so using that threshold of 0.05, we're then going to look at the degrees of freedom on the very left-hand column, 21. And then we're going to come over and we're going to find where those things intersect. And they intersect at 2.080. 2.080 is then our critical value. So that's what we're going to be comparing our test statistic to. So we have a critical value of 2.80, and then we have a test statistic or a t-value of -3.109. And so R is going to be doing some comparisons to see whether or not we can reject our null hypothesis based on this comparison that I'm going to walk you through now. So again, our test statistic is 3.109, and we'll do plus or minus because it's two-tailed. So essentially what we're saying is, if you look at the normal curve and we have our number line here at the bottom, the 3 is going to be plus or minus. So we're going to have, you can think about our value being out on the tails, way out on the tails at -3. And then we're going to compare whether or not that's outside or more extreme than our t-value of -2.080. And so we know that if 2 is right here on the number line, -2 is right here on the number line, and our value is out here at -3, we are indeed more extreme or outside of that. So we can actually reject the null hypothesis. So we really just need to know if our test statistic is more extreme than the critical value set by the degrees of freedom and the statistical significance threshold that we care about. Okay, let's just kind of reiterate that one more time, and you can kind of watch this as well. We have a test statistic of 3.109. All right, we have a critical value of 2.080. I want you guys to think about putting that on a number line with our normal distribution above it. And we need to see how far out in the tails we are with our test statistic and whether or not our value is more extreme than the critical value that we've set based on the degrees of freedom, right? Our degrees of freedom here, which was 21, and the statistical significant threshold that we met here, which is 0.05. Okay, and we know based on this number line that our plus or minus 3.109 is outside of that critical value kind of window between plus or minus 2.080. Okay, so we just need to know if it's more extreme or not. So because of this, we get a p-value of 0.005306. which in this case, we can just round it down based on the information we've garnered from here, which means we can reject our null hypothesis and have some evidence that we actually do see some sort of relationship between major and midterm scores. So we have some evidence in this case that those who are political science majors do a bit better on their midterms than those who are non-majors. And again, we can get both the means for each group, and we can say that those are systematically different from each other, right? So there's a statistical difference between the mean of majors and the mean of non-majors. So there's something going on, right? We can talk about the causal mechanism here for days, right? Between what happens when somebody in the major takes the test and a non-major does, right? So we can talk about all the different reasons why maybe majors are more interested and invested. They want to get to know that professor better and perform better for that professor because they're in that same major. So there's a lot of different reasons why this might be happening. We don't need to talk about the confidence interval yet, but in future lectures, we're going to talk about this p-value and why it matters. I'll give you a functional definition for it. But again, in this test statistic output, the things that you should be thinking about is what's happening under the hood. We get our t-value of -3.109. We have degrees of freedom that help us assess what our critical value is, and that critical value is the number that we compare our test statistic to on the normal curve in order to determine whether or not we think we have a statistically distinct effect happening here. Okay, this was a lot of information. The big things I want you guys to think about moving forward is that your t-test is what you can use when you have a categorical binary independent variable and an interval ratio dependent variable. It's what you want to use when you want to compare the means for two groups. So say you wanted to compare the average of a certain political attitude between Democrats and Republicans. Perfect example to use a t-test. And so moving forward, I want you guys to understand that conceptually. And then as best as I can, I want you guys to try to understand what's happening under the hood in terms of the test statistic and comparing it to the critical value on this sort of normal distribution curve. But I do definitely understand that that stuff is a little bit more difficult. And so I want you guys to be thinking about the best way to kind of start to assess how we think about inferential statistics on the normal curve as well. But again, I think the big things that I want you guys to take away from this lecture are when we can use t-tests, right? When we have the IV that's categorical and the DV that's interval ratio, and then maybe a little bit of how to understand and interpret the difference between those means.